In the previous lesson, we learned the basic components of the 4-axis robot control circuit and the parameters and settings required for PLC control of the 4-axis robot. In this lesson, we will continue with the fundamental elements of programming required for PLC control of the 4-axis robot. 3. PLC programming for 4-axis robot motion control. 1. Common instruction analysis. 1. Axis Enable Program. Axis Enable Disable is implemented using the MC power instruction. A. Instruction format, as shown in the figure. B. Parameter description. Enable an input parameter. When set to 1, the axis is enabled. When set to 0, the axis is stopped and disabled. Start mode, an input parameter. When set to 1, it enables a position-controlled axis. When set to 0, it enables a non-position controlled axis. This parameter defines whether the axis has feedback control over its position. Stop mode is also an input parameter, which specifies the axis's stopping mode. When set to 0, the axis performs an emergency stop. When set to 1, the axis stops immediately at a specified deceleration rate. When set to 2, the axis performs an emergency stop with jerk control. Status is an output parameter that indicates the axis enable state. False means the axis is disabled. True means the axis is enabled. Busy is an output parameter. When set to true, it indicates that the MC power instruction is active. Error is an output parameter. When set to true, it signals that an error has occurred. Error ID is an output parameter that indicates the output address of the error. C. Parameter settings. Create an axis parameter data block as shown in the figure, with the data type set to MC axis type. The specific parameter settings are illustrated in the figure. Set enable to true and start mode to 0, which configures the axis as non-position controlled. The initial value for stop mode is set to 0, meaning the axis will stop using the emergency stop mode. Output parameter signal states are automatically displayed during program execution based on the output results. 2. Axis stop control. The MC halt instruction is used to stop the axis. A. Instruction format, as shown in the figure. B. Parameter description. Axis, an input parameter that specifies which axis to stop. Execute, an input parameter. The rising edge of this signal triggers the axis to stop. Done, an output parameter that indicates whether the axis speed has reached 0. When set to true, it confirms that the speed is 0. Busy, an output parameter indicating whether the command is currently being executed. When set to true, it indicates that the command is currently being executed. Command aborted, an output parameter indicating whether the command execution was aborted. When set to true, it indicates that the command execution was aborted by another command. Error, an output parameter. When set to true, it signifies that an error has occurred. Error ID, an output parameter that provides the output address of the error. C. Parameter settings. Initial values for the parameters should be set as shown in the figure. 3. Manual control of axis. The MC move jog instruction is used for manual control of the axis. A. Instruction format, as shown in the figure. B. Parameter description. Axis specifies the axis to be controlled. Jog forward, an input parameter. When set to true, the axis moves forward at the speed defined by the velocity parameter. Jog backward, an input parameter. When set to true, the axis moves backward at the speed defined by the velocity parameter. Velocity, an input parameter defining the preset speed limit for jog mode. Start or stop speed less than or equal to velocity, less than or equal to maximum speed. Position controlled, defines whether the operation is position controlled. False indicates non-position controlled operation. True represents position controlled operation. In velocity, an output parameter, when set to true, it indicates that the axis has reached the velocity specified in velocity. Busy, an output parameter. When set to true, the command is currently being executed. Command aborted, an output parameter. When set to true, it indicates the command execution was aborted by another command. Error signals an error occurred during command execution. C. Parameter settings. Initial values for the parameters should be set as shown in the figure. 4. Homing programming. The MC home instruction is used to return the access to its home position. A. Instruction format, as shown in the figure. B. Parameter description. Access, an input parameter that specifies which access to home. Execute, an input parameter triggering the command execution on a rising edge. Position, an input parameter. For mode equals 0, 2, or 3, this sets the absolute position of the axis after homing. For mode equals 1, it defines a correction offset for the current axis position. Valid range. -1.0 E12 is less than or equal to position, which is less than or equal to 1.0 E12. Mode, an input parameter determining the homing mode. 0, direct homing, absolute, sets the axis position to the value specified in position. 1, direct homing, relative. The new axis position will be the current position plus the value in position. 2, passive homing. Homing behavior is determined by axis configuration. After homing, the axis position is set to the value in position. If axis name.statusbits.homing done equals true is referenced, this status bit remains set during the additional passive homing operation. 3. Active homing performs homing based on the axis configuration. After homing, the axis position is set to the value in position. 6. Absolute encoder calibration relative sets the current position offset to the value in position. The calculated absolute offset is persistently saved in the CPU. Axis name.statussensor.abs encoder offset. 7. Absolute encoder calibration absolute sets the current axis position to the value in position. The calculated absolute offset is persistently saved in the CPU. Axis name.statussensor.abs encoder offset. Done, an output parameter. True indicates that the command has completed. Busy, an output parameter. True indicates that the command is being executed. Command aborted, an output parameter. True indicates that the command execution was aborted by another command. Error, an output parameter. True indicates an error occurred during command execution. For more information on the cause of the error, refer to error ID and error info. Error ID, an output parameter that indicates the ID address of the error if error is true. Error info, an output parameter that provides error information when error is true. C. Parameter settings. Set position to 0, which means the robot axis coordinate will be set to 0 after completing the homing process. Set mode to 3, indicating active homing will be used to return the axis to its reference point. Other parameter initial values are shown in the figure. 5. Robot control instruction. Absolute motion control instruction format. A. Instruction format, as shown in the figure. B. Parameter description. Velocity, an input parameter specifying the speed at which the axis moves. The value must lie within the range. Start or stop speed less than or equal to velocity, less than or equal to maximum speed. Direction, an input parameter defining the direction of axis movement. Note, this parameter is ignored for axis controlled by PTO, pulse train output. Done, an output parameter indicating whether the axis has reached the target position. True indicates the axis has reached the target position. Busy, an output parameter indicating whether the command is being executed. When set to true, it indicates that the command is currently being executed. Command aborted, an output parameter indicating whether the command execution was aborted. When set to true, it indicates that the command execution was aborted by another command. Error, an output parameter. When set to true, it signifies that an error has occurred. Error ID, an output parameter that provides the output address of the error. 2. Programming and analysis of 4-axis robot axis motion control. 1. Create the axis control module. As shown in the figure, a subprogram and control data block are created. 2. Program the main control logic for the 4-axis robot axis. Network 1. The MC power motion control instruction is used to enable or disable each axis. The MC power instruction must be continuously called in the program and should always be called before any other motion control instructions. First, set the enable signal for each axis to 1 to activate them. Start mode settings. This parameter is ignored when using positioning axes driven by PTO. Since the robot axes are PTO controlled, this parameter can be disregarded. Set stop mode equals 0, which corresponds to emergency stop, i.e., stop the axis using the emergency stop speed or time set in the axis technology object parameters. Other control variables are written to the corresponding locations sequentially. Network 2 calls the axis stop subprogram FC2. When the external parameter of stop equals 1, all axis stop. Network 3 calls the axis manual operation subprogram FC3. When the variable db6 data from pc.jog or auto equals 1 from the external main control system is received, this subprogram runs. Network 4 calls the homing subprogram FC6 for each axis. Network 5 calls the robot coordinate movement service subprogram FC10. 3. Subprogram FC2 stop control subprogram for each axis. Network 1. When an emergency stop signal is received, all axis stop execution signals are set to 1. Network 2. A-axis stop control. First select the axis stop instruction. Set the axis to A, and write each output terminal to the corresponding variable in the A-axis data block. When there is a signal input at the execute terminal, the stop command for the A-axis is executed. The rising edge of the A-axis stop execution variable dbaxisparam.aaxis.mchalt.execute triggers the signal input to the execute terminal. Networks 3, 4, and 5. These define the stop control instructions for the X, Y, and Z axis respectively. The programming method is the same as that used for the A-axis stop control. 4. Subprogram FC3. Manual operation control subprogram for each axis. Network 1 checks whether it is in manual mode. If not, the program jumps to the section marked YENDI. Network 2, A-axis manual operation control, calls the MC move jog instruction, sets the axis to A, and configures the jog forward, jog backward, velocity, and position controlled variables. Manual forward and backward control is managed by dbaxisparam.aaxis.mcmovejob.jogforward and dbaxisparam.aaxis.mcmovejob.jogbackward, which receive signals from external manual buttons. Velocity is controlled by dbaxisparam.aaxis.mcmovejob.velocity, and its initial value can be set as needed. dbaxisparam.aaxis.mcmovejob.position determines whether position control is used. When set to 1, position control is enabled. When 0, it is disabled. Other terminals are filled with corresponding variables from the dbaxisparam data block, as shown in the figure. Networks 3, 4, and 5 define the manual operation control program for the X, Y, and Z axes respectively. The programming method is the same as for Network 2. Network 6. If manual mode is not set, but the current axis is still running in manual mode, the manual mode flag signal is output as 1. 5. Subprogram FC6. Homing control subprogram for each axis. Network 1. A-axis homing control. Calls the MC home instruction, sets the axis to A, and configures position and mode variables. Set the position parameter, home position, to 0 and the mode parameter to 3 to use active homing mode. The rising edge of the A-axis homing execution variable dbaxisparam result.axis.mchome.execute triggers the signal input to the execute terminal to initiate homing. Other terminals are filled with corresponding variables from the db_access_perm data block, as shown in the figure. Networks 2, 3, and 4 define the homing control programs for the X, Y, and Z axes, respectively. The programming method is the same as for Network 1. 6. Subprogram FC10, motion control for each axis. When the move to target step is set to 1 and stop is set to 0, the enable signal is set. When the move to target step is 0 and stop is 1, the enable signal is reset. Network 2, update service code. When enable is active and #move result.service code equals 0, the current motion step is passed to the motion result. The default position of the robot points toward raw material number 7, with the gripper in the retracted state. Network 3, move to position below start point. When enable is active and the motion step is at step 1, the motion execution control variables for the X, Z, and A axes are set to 1. At the same time, the target positions for each axis, as determined by the host computer, are assigned to the respective position terminal control variables for each axis to define where each axis should move. Next, absolute positioning instructions are programmed for each axis. Set the axis parameter to X, Z, or A, respectively. Set the position parameter to the target location for each axis, provided by the host computer. Set the velocity parameter as needed, ensuring it falls within the range between the maximum speed and stop speed. Configure the direction parameter according to the control flow provided by the host computer. Other terminals are filled with corresponding variables from the db_access_perm data block, as shown in the figure. This completes the movement of the X, Z, and A axis to the position just below the start point where the gripper remains retracted. Network 4. Check if reached the start position. This network checks whether step 1 of the motion sequence has been completed. If so, set the motion step control variable to 2. When enable is active, the motion step control variable is 1, and the move complete signals for the X, Z, and A axes are all 1. Step 1 is considered complete. The motion step control variable is updated to 2. Network 5. Extend the gripper. When enable is active and the current motion step is step 2, set the Y-axis motion execution control variable to 1. The target address for each axis, provided by the host computer, is assigned to the position terminal control variable for the Y-axis to define its desired movement position. Following the same procedure used for the X, Z, and A axes, the appropriate control parameters are configured to complete the gripper extension operation. Network 6. Check gripper extension completion. This network checks whether step 2 of the motion sequence has been completed. If so, set the motion step control variable to 3. When enable is active, the motion step control variable is 1, and the Y-axis move complete signal is 1. Step 2 is considered complete. The motion step control variable is updated to 3. Network 7. Lift the pallet. When enable is active and the current motion step is step 3, set the Z-axis motion execution control variable to 1. The target address for the Z-axis, provided by the host computer, is assigned to the position terminal control variable to define its desired movement position. Following the same procedure used for the Z-axis, the appropriate control parameters are configured to complete the pallet lifting operation with the extended gripper. Network 8. Check pallet lifting completion. This network checks whether step 3 of the motion sequence has been completed. If so, set the motion step control variable to 4. When enable is active, the motion step control variable is 3, and the Z-axis move complete signal is 1. Step 3 is considered complete. The motion step control variable is updated to 4. Network 9. Retract the gripper. When enable is active and the current motion step is step 4, set the Y-axis motion execution control variable to 1. The target address for the Y-axis, provided by the host computer, is assigned to the position terminal control variable to define its desired movement position. Following the same procedure used for the y-axis, the appropriate control parameters are configured to complete the gripper retraction operation. Network 10. Check gripper retraction completion. This network checks whether step 4 of the motion sequence has been completed. If so, set the motion step control variable to 5. When enable is active, the motion step control variable is 4, and the y-axis move complete signal is 1. Step 4 is considered complete. The motion step control variable is updated to 5. Network 11. Move A-axis, then X-axis, then Z-axis, offset +40. No gripper extension. When enable is active and the current motion step is step 4, set the A-axis motion execution control variable to 1. The target address for the A-axis, provided by the host computer, is assigned to the position terminal control variable to define its desired movement position. Then, the absolute positioning instruction for the axis is called. According to the method described previously, the parameters are configured to complete the A-axis motion instruction. Once the A-axis movement is complete, set the X-axis motion execution control variable to 1. The target address for the X-axis, provided by the host computer, is assigned to the position terminal control variable to define its desired movement position. Again, the absolute positioning instruction is called, and parameters are set as described earlier to complete the X-axis motion. Once the X-axis movement is complete, the Z-axis motion control logic is programmed following the same approach used for the X-axis, completing the movement of the Z-axis. The details are as shown in the figure. Network 12. Check movement completion. This network checks whether step 5 of the motion sequence has been completed. If so, set the motion step control variable to 6. When enable is active, the motion step control variable is 5, and the Z-axis move complete signal is 1. Step 5 is considered complete. The motion step control variable is updated to 6. Network 13. Extend the gripper to the position above the target point. When enable is active and the current motion step is step 6, set the y-axis motion execution control variable to 1. The target address for the y-axis, provided by the host computer, is assigned to the position terminal control variable to define its desired movement position. Following the same procedure used for the y-axis, the appropriate control parameters are configured to complete the operation of extending the gripper to the position above the target point. Network 14. Check if gripper has reached the position above the target point. This network checks whether step 6 of the motion sequence has been completed. If so, set the motion step control variable to 7. When enable is active, the motion step control variable is 6, and the y-axis move complete signal is 1. Step 6 is considered complete. The motion step control variable is updated to 7. Network 15. Move to the target point. When enable is active and the current motion step is step 7, set the Z-axis motion execution control variable to 1. The target address for the Z-axis, provided by the host computer, is assigned to the position terminal control variable to define its desired movement position. Following the same procedure used for the Z-axis, the appropriate control parameters are configured to complete the operation of moving the Z-axis to the target point. Network 16. Check if reached the target point. This network checks whether step 7 of the motion sequence has been completed. If so, set the motion step control variable to 8. When enable is active, the motion step control variable is 7, and the Z-axis move complete signal is 1. Step 7 is considered complete. The motion step control variable is updated to 8. Network 17. Z-axis moves down 10 mm, Y-axis retracts. When enable is active and the current motion step is step 8, set the Z-axis motion execution control variable to 1. The target address for the Z-axis, provided by the host computer, is assigned to the position terminal control variable to define its desired movement position. Then, the absolute positioning instruction for the axis is called. According to the method described previously, the parameters are configured to complete the z-axis motion instruction, moving the z-axis downward by 10 millimeters. Once the z-axis movement is complete, set the y-axis motion execution control variable to 1. The target address for the y-axis, provided by the host computer, is assigned to the position terminal control variable to define its desired movement position. Again, the absolute positioning instruction is called. Based on the earlier configuration method, the necessary parameters are set to complete the y-axis retraction operation. Network 18. Z-axis moves down 10 millimeters, y-axis retracts. Check completion status and readiness to proceed to next step. 5. Task implementation. 1. Design the servo control circuit for the 4-axis robot and perform installation and commissioning. 2. Properly configure the motion control parameters for PLC-based control of the 4-axis robot. 3. Correctly program the PLC control logic for the 4-axis robot and perform validation and debugging. This lecture ends here. Thank you.